Hi there. I'm back again, and here we're going to talk about using Castigliano's theorem. Now, if you are watching this video thinking you're going to get background on the derivation of or the theory behind Castigliano's theorem, you are in the dead wrong place. Please go find another video. I haven't made one yet as of when I'm making this one. I may down the line, right? Probably will, knowing me. What I'm doing today is I'm talking more about, if you know Castigliano's theorem, how do we make sure we're using it correctly, okay? If that thing I've written on the right here, this delta A equals the partial of U divided by Q, okay, where Q is applied at point A, I can probably write that. If that doesn't mean anything to you, you're in the wrong video. Seriously. Give you a sec. Okay, those of you who are here are now in the right video. You know what that statement means, right? You want to know, well, how do I know I'm doing it right? Okay, I find there's three basic rules to using this. The first rule is to use an appropriate force. This is actually the toughest rule, right? It comes in three subparts. We'll see that in a few minutes. Okay. The second rule is then to include all the strain energy. It's easy to forget parts, right? See, students, on one of the homework problems I assign, try to kind of cheat the system because they realize, ooh, if I do this, it all works and we're great. We get the right number. Yay! But you left out a large source of strain energy, which it is on you to prove is zero, or zero contribution, I should say, to the overall deflection. If you don't do that, you've done it wrong. Okay? And the third thing is substitute values at the proper time. There isn't just one time to do this. I don't want you to think if you do it too soon or if you do it too late, you're stuck, right? It's not that bad. You just got to do it late enough, right? If you do it too soon, you're in trouble. You do it late enough, fine, right? You can do it anywhere between a certain point and when you get to the end, right? Just can't do it too soon. All right, so let's look at each of these. What do I mean by use an appropriate force? And to illustrate this, I've got this set up, right? I've got a horizontal rod, horizontal bar, let's say, actually is a better way to put it. And I feel better about this if I have axes in here so I can talk about the X and Y directions, okay? So I've got a horizontal bar. I'm just saying it's made of aluminum. Why am I saying that? I'm not going to solve this, so it doesn't matter in that sense. The sense in which it matters is to make sure we know this is not a rigid thing, right? This is going to bend. The steel rod that's coming down from D to B is going to stretch. I know both of those are going to store strain energy, okay? That's why I want to make sure we know they're made of some real materials, not some rigidium or something, okay? Yes, infinitely rigid material, rigidium. I have other names for it, but that just depends on the student I'm in front of. Anyway, so one was use an appropriate force. Okay, what makes an appropriate force? Aha. This is where the three sub-rules come in, okay? And I'm not going to follow outline etiquette here. I'm going to make up my own thing. I'm going to use those little Roman numerals, right? 1, right? Applied at the correct place. Hopefully you know, and again, if you don't know this, you're probably in the wrong video, but hopefully you know, for example, that you have to apply the force at the point of interest, because that derivative I had above, that delta A equals partial U with respect to Q. Castigliano's theorem says that that partial derivative of strain energy with respect to force gets you the deflection at the point where the force is applied, right? Well, there's more to it than that, but I'm stopping there because that's what I'm on right now, is apply the correct place. So what that means is I've got this external, this nice force Fc, right? This force applied to the end Fc. If I want the deflection of point B, I can't use it. It's not at B. If I want the deflection at point C, great, I'm fine, right? But I can't use a force at C to find deflection at B and vice versa. I can't use the force at C to find the deflection at point A, which hopefully is 0. It's supported, for crying out loud, right? So there we go. And actually, let's make sure that I intended that to be a pin. Let's make sure that appears as kind of a pin. There we go. All right, just want to make it simple. I don't want this to be statically indeterminate, right? Not throwing that monkey wrench into this, right? So yes, if I want the deflection at point B, I need a force at point B. Done and done. I can't use the force at C to find the deflection at B. I can use the force at C to find the deflection at C. Okay, so that's the first point to what makes an appropriate force. The second point is that force must be applied in the proper direction. If I want the horizontal deflection of point C, I am out of luck, right? I need to add something else. That's where that dummy force Q comes in, right? I always call it Q. You may call it something else. That's fine, okay? If I want the horizontal deflection of point C, I need a horizontal force at point C. I don't see one. That's when you add one in, okay? That's what the second point says. It has to be at the right place and in the right direction. Then there's the third point. The force must be external. External. Why does that matter? Okay, let's take this piece up here. I scrolled away from it. I shouldn't have yet. Let's take this piece that I drew, right? This little sample steel aluminum combo, and let's break it into its parts and see what I mean and see what we mean by external in this case. Okay, so I'm going to say FBDs, free body diagrams, but I'm only going to start off with one, and my free body diagram is going to be perilously simple. That's how I usually draw a horizontal bar, right? If I don't care about the width dimension, why should I bother drawing it? And I would certainly have a reaction AY. I can have a horizontal reaction FC. I can have that's applied, and I'm going to have a force in there. Let me call it F sub BD, okay? What that force is, of course, is the force from the rod on the bar. And if you're not thinking of this 100%, you might see FBD and say, ooh, look, I can use that. And no, you can't, right? And to understand why, I have to turn around and take one extra step. I have to draw the other free body diagram. I said there was a plural there, right? It wasn't because I just like drawing S's. Here is bar, rod, I should say, BD. And I'm going to, I think you'll agree, have force BD in the bottom. That'll be opposed by PDB on the top. PBD, there we go, right? And actually, I'm missing one very important thing in my free body diagram. Hopefully, I'd have a class full of students yelling at me that I didn't put axes on this thing, right? And there we go. So notice how FBD, that same force, that internal force, because of Newton's third law, is equal and opposite on BD compared to what I did on ABC. Okay? That's point A, that's point B, that's point C. It appears here and there. So now wait a minute, right? You remember that partial derivative on the first page? The derivative of energy with respect to that force applied in the right direction is at the right point, I should say, in the right direction, is the magnitude of the deflection in the direction of that force. FBD is in both directions. You could look at the left one and say, oh, it's going up if I get a positive result. I could look at the right-hand one and say, oh, it's going down if I get a positive result. And we can't decide. We literally cannot decide because it's going up on one free body diagram and down on the other. There is no tiebreaker in this case. You can't use the force because it appears in both directions. Now, the fun thing is, if I turn around, and this is how we know we have a force that we can use, and I apply a dummy force Q to this, my free body diagram of the right-hand bar does not change, right? What you'd find is that your sum of forces in the vertical direction changes. What do I mean? Well, let's leave there. That's just enough, okay? Back to blue. With no Q, if I sum forces in the y direction, set that equal to 0, equilibrium says that's supposed to happen, right? AY plus FBD minus FC equals 0. FBD is equal to FC minus AY. And that's what would go into bar BD on the right. With Q, same sum of forces in y equals 0. I'm going to have, I have to scroll down, dang, right? AY plus F in BD minus FC minus Q equals 0. Ta-da, right? FBD is equal to FC plus Q minus AY. Q makes an appearance inside FBD, but notice how Q does not appear on the free body diagram of BD at all. It's only on the free body diagram of ABC, right? And the value of force BD changes based on having that Q. Yes, then we would take the derivative and set Q equals 0, and then we go away. It's fine, I agree with that. But this is an important distinction, because without Q in there, I would be using a force. If I took the derivative with respect to FBD, the force in BD, I have a force that has two directions. This Q appears once and is in one downward direction. We get a negative result, we know the thing's moving up. We get a positive result, we know the thing's moving down. No argument. No possible rational argument. That's what makes an external force, okay? That's one thing I see people mess up. All right, so I said you have to choose an appropriate force. Second one was essentially take all strain energy. So for this system that I've drawn, U in this case is equal to the strain energy of bar AC plus strain energy of rod BD. You can't leave one or the other of them out. You can't say, ooh, I'll use FBD, and then I'll just leave out the fact that AC is there at all. That's why, again, that's what I see students try to do on a homework problem that I give. And they're wrong, okay? You have to include all the strain energy. Yes, BD, being that it's a rod being stretched axially, I would call this P squared L over 2AE. UAC, I would not compute, right? What I would do is I would use the derivative, right? And let's just call it the partial. Let's say I'm looking for the deflection of point B, partial U with respect to Q, is equal to partial UAC partial Q plus partial U BD. Let me make that smaller. Let's make my subscripts into subscripts, right? Plus partial U BD partial Q, where for the AC thing, because it's a moment situation, right? This is bending. We would use 1 over EI integral of moment as a function of x, partial moment, partial Q dx. Fine, we would do that, right? I would never compute the strain energy of a beam in bending. It doesn't make any sense to do to me. I just want to take a derivative with respect to a force anyway, so let's just cut to the chase, okay? I see people leave out one or the other of these. We need both. If it can support a strain, if it's going to stretch or deform or twist or whatever it's going to do, right? If it's bending, if it's twisting, if it's stretching, it needs to be included in the strain energy. No questions asked. It needs to be accounted for, okay? If you leave it out, you've done it wrong. So make sure you include the strain energy of every part. That's why I'm a huge fan, scrolling up, of drawing all the free body diagrams. That reminds me, ooh, I have AC that's bending, and I have BD that's stretching. Why don't I account for both of them? Right? That's what that tells me. Last but not least, okay? take the derivative. Sorry, we substitute values at the proper time. Yeah, I jumped ahead of myself there. I apologize. Substitute values at the proper time. What does that mean? That means best practice, you do not substitute a value, especially if you have a dummy force Q in there, right? You don't go substituting a single value like that until you've taken the derivative. Bottom line, take the derivative, right? In this case, here would be delta U by del Q, right? Partial of U with respect to Q. And that would be U of the whole thing. And then, and only then, you substitute your value. Whether it's 0 for a dummy force, whether it's a known value, if we had FC that we were using, maybe it's 100 pounds, sure, then we would substitute 100 pounds after the derivative, right? If we wanted to find the deflection of point C, we'd use FC. I wouldn't use a Q, I'd use FC, right? But you take the derivative and then you substitute the value. Why is that? Because if you put in the value first, you'll see a number. And you'll say, ooh, derivative of number with respect to Q is 0. I got 0. And you got it wrong, right? You have to take the derivative, leave things as variables. I know a lot of students don't like to do that, but gosh, it's your friend, okay? Leave them in as variables, take a derivative, and then put the value in, okay? So those are my 3 basic rules for making Castigliano work, okay? In review, 1, you have to use an appropriate force. That's a force that's applied at the right point, applied in the correct direction, and is external. And people mess up the third one, the external part, more than the other 2. Figuring out the force has to be at the right point in the right direction is easy. External can be a little bit less so, a little bit more subtle. Number 2, you have to take the strain energy of everything that's stretching. You have to include all the strain energy, right? That means solving for everything in terms of the force that you intend to take the derivative with respect to, okay? Think ahead. You've got a Q force in there. Make sure that everything is in terms of Q. You've got some external force like the FC that I had above. Make sure everything's in terms of FC. Then take the derivative, and only after that point, substitute in a value, right? Do not put in numbers until you get past that derivative. That is your magic wall, the line that you cannot cross. Values cannot go in for the force you're taking the derivative of until you have done the derivative, right? Otherwise, you'll get zeros where they don't belong, and unhappiness will result. You won't get it right. You'll be unhappy, right? Those are the general questions, or the general points, I should say, the general rules for using Castigliano. Hope this helps. And again, thanks a lot for watching.